So before we dive into the detail around reflow soldering, I do have 2 slides of corporate presentation just to show where Datapaq fits within our larger organization. As you will have noticed, all of the slides have a Fluke Process Instruments logo. Datapaq, founded in 1984 in Cambridge in the UK, focused completely on design and manufacture of temperature profiling systems. And our R&D teams for mechanical, electronic and software disciplines are still based here in Cambridge, along with our order management team for Europe and Asia. And we started out making these profiling systems for use in the coating industry, as one of our founders came from that industry, in particular around coating the insides of beverage cans. And the issue there was around coating adherence to the metal, and I don't want to say arguments, but discussions that took place between coating suppliers and applicators as to when they came to troubleshooting the process. And I think all of you electronics industry see it similar, where often the expertise of the paste supplier is called on to assist in the process of troubleshooting, and that's directly analogous to the coatings industry and where we started. We've also taken that concept and applied it to industrial processes through cooking chicken, right through electronic soldering, heat treatment of steels, through to the high temperature firing of ceramics. And Datapaq, along with Raytec and Ercon, was brought together in 2015 under the Fluke Process Instruments banner. So we all operate under the Fluke Corporation, which in turn is owned by Fortive, which is a large industrial group with over 20 operating companies and 24,000 employees around the world. For profiling, as I said, Datapaq based in Cambridge in the UK. Our data loggers and systems are manufactured and shipped from the Raytec operation in Berlin. So designed in Cambridge, manufactured in Germany. We have sales support and service centers in Shanghai and also in Washington, USA, where the Fluke office there is based in Everett. We also have sales office at other locations around the world supporting our regional customers and, of course, the extensive distributor network. So I alluded to this earlier. Datapaq divides the whole world into, or the whole heat treatment world into 6 segments. And today we're really focusing on this one around the electronics industry, and even more, the focus is really around the use of temperature profiling in reflow soldering ovens. We also have systems that can be used in vacuum soldering, vapor phase soldering, wave soldering, conformal coating curing. And some of the points discussed today will be common to those other mass soldering techniques. So, systems for the electronics industry, reflow tracker, a data logger in a thermal barrier passing through a reflow oven, typically measuring product temperature. That's what 80%, 90% of all the customers or users are doing with reflow tracker systems. And you can see here the basic components of a reflow profiling system. Also on the screen, you'll see a product called a surveyor. This is a tool for measuring process stability. So this is fixed sensors passing through the oven regularly. And we'll come back to this a little later in the presentation. Measuring product temperature in reflow soldering is great, and most people are using golden boards to do this with thermocouples attached to them. But there is a degradation in those boards when they're used 10, 20, 30 times. And products like the surveyor that are available from a number of suppliers have fixed sensors on that enable you to get a more stable reading system, if you like, measurement system. And then at the bottom, a range of accessories for measuring those other processes. Okay, in detail, a quick slide to talk about the data logger. The Datapaq DP5 is a battery-powered data logger designed specifically for use in the electronics industry. It's, I think, the third or fourth generation of Datalogger for this industry. It has some features that the previous generation didn't, and it was particularly designed to keep cost of ownership low. So this unit will recharge its battery from any USB outlet via a standard USB cable. It uses off-the-shelf Type K thermocouples that can be obtained anywhere. And the battery itself is user replaceable. So when it does eventually get tired, as we all do, it can be replaced by the user, and no calibration or information in the logger is lost at that point. Around the battery, this is one of the issues with data loggers. We can fully charge the battery in 90 minutes from discharged, and there's a fast charge controller in there, and that will measure the current going into the battery and also the temperature of the battery. But if you purchase a very low cost USB cable, you'll find the wires in the cable have a small cross section, and then fast charging through that cable becomes difficult. So although cables can be purchased anywhere, just take care to get a quality one, because if you get a very small USB cable, you can find the voltage drop down it will cause the battery charging circuit to malfunction. No damage is caused, but the logger will recharge much slower than you expected. The batteries are fully rated to 85 degrees centigrade, at which point the logger will shut off and will warn the user that it's been heated. And the idea of warning you is to try and prevent it happening again. Heat cycling batteries is not particularly good for them. It does shorten their life. So any overheating should be investigated and avoided in the future. This logger does have a Bluetooth communication capability. Now, this can be used as a cable replacement for your communication with a laptop, so you can reset and download information just using the Bluetooth communication. And the range on that is up to about 10 meters, because although the logger is in a solid machined aluminium case, it does have a Bluetooth window at the end, a non-conductive window to allow the signal out, so we can get a 10-meter range. That's enabled us to profile a number of reflow ovens, getting data in real time using Bluetooth as the logger passes through the oven. You know, we can't guarantee that you'll get reception through your process, but we've tested this in a number of reflow ovens and some wave soldering applications, and we've got very good reception. So if you do need real-time data from the data logger in the process, always worth trying the Bluetooth option. It may just work for you, and if it does, that's all the better. The software to support that is shipped with the standard software. So much for the data logger and some hints around the battery. Now I want to look at the thermal protection. I've got 2 or 3 slides here talking about thermal protection. Although this process is relatively low temperature compared to others that profilers are used in, there is a tendency to profile much more frequently in this industry, and care has to be taken around cool down times to ensure that the logger doesn't get overheated. The thermal barriers themselves use a microporous ceramic insulation, and that's about the best insulation you can get. It's also used in our thermal protection systems for anything up to 1200 centigrade. It's exactly the same material. We just use a lot more of it on those larger systems. Now, there's an advantage of using the insulation is that the thermal barrier will absorb very little energy. So it will cool down quickly for reuse. This particular thermal barrier you can see on the screen will open up completely flat. So when it exits from the oven, open it up, the lid and the base will be flat onto the floor or the surface, and it will cool down very quickly that way. Place it on a conductive surface and the heat will dissipate back out of the barrier very quickly. In addition, using that very good insulation ensures that little heat energy is taken from the oven. For those of you that have got a reflow oven where you can monitor the power being taken by the heating elements in each section, you can pass through some thermal barriers from some of our competitors, and you will see the power increase on the zone as the thermal box goes through the zone. And that's the energy being absorbed from the oven as the barrier goes through. Systems like that take a lot longer to cool down when they come out. So I thought I'd add this slide as we're all at home and helping the children with the homeschooling. We'll look at heat conduction. In heat conduction, there's three principal methods: conduction, convection, and radiation. And if we look at our microporous insulation, it's essentially a sintered material made from small spheres. So the spheres have a point contact, which makes the conduction paths very long. So we're reducing heat conduction through the insulation that way. The degree to which it's compressed controls the size of the cavities between the spheres. And there's very careful control on the compression to ensure that convection within those cavities is reduced to a minimum. And to reduce any radiative heat transfer within the material itself, the spheres are coated with a reflective pacifier. So that's how the microporous insulation in the thermal barriers is working to reduce as much as possible heat conduction through to the data logger. One final slide on this topic, looking at cool down times. So if you're troubleshooting or you're setting up for a new process, there's a tendency to pass the system through very rapidly, one time after another. This slide just shows the results of an experiment we did here, where we heated the data logger up to 80 centigrade, so maximum operating temperature, and then measured the time to cool. When we placed the logger on a thin metal filing cabinet to cool back down from 60 to 35 degrees, took in the region of 12 minutes. When we did exactly the same thing, but placed the data logger on a thick steel plate, a nice cool surface, cooled down in 3 minutes, or 3.5 minutes. So you can see, once the data logger is out of the end of the oven, place it on a cold conductive surface. If you've got one available, that's great. If not, put it over some fans. You'll cool it down in 3 or 4 minutes, which, by the time you've downloaded, had time to analyze the information, you can be ready to conduct another profile run. And finally, within the software, there is the ability to prevent the logger being reset if it hasn't cooled down. It's not set up by default, but you can go into the options of the software and set yourself up a limit so that if you have inexperienced operators using it and they have a tendency to put the data logger back around the system before it's cooled, you can set this up and prevent them damaging the logger by putting it back through. This will actually prevent it being reset and provide a warning to the user. Okay, that's my slides on thermal protection. It's an important subject, even though this is low temperature. We do see a tendency for people to overuse the systems. Thermocouples. I have 4 or 5 slides on thermocouples today. These are the typical thermocouples that are used within the industry, fairly lightweight. The 0.2 millimeter wire you see at the top is an industry standard, really, a sort of a default, if you like, that's used everywhere. It's a good compromise between a rugged solution and one that provides an adequate thermal response. The glass fiber is the same internal wires with a different insulation used for higher temperatures. If you're going above 265 centigrade, you really need to avoid the PTFE insulation and move over to glass fiber. And the picture at the bottom shows a very fine wire, so a 0.1 millimeter wire that can be used to attach to balls on VGA devices. All of the thermocouples supplied are to special limits of error, which in our case will be plus or minus 1.1 degrees centigrade. as I said earlier, they've all got standard thermocouple plugs on the end, so you can buy your thermocouples anywhere. Just be careful when specifying them that you do buy to special limits of error. If you just buy the standard thermocouples, then they'll possibly be supplied to the standard limits, which would be double. So your uncertainty would go from ±1, ±2.2. Some do's and don'ts with thermocouples. It's typical in the industry to connect a number of thermocouples to a golden board and store it in the cupboard and use that when you come to make another batch of that particular product. When a thermocouple breaks, there's a temptation just to twist the wires together and stick it back on and do the profiling. That works, but you must understand that the temperature is measured at the first point that the two wires of the thermocouple touch each other. So if you've made a long twisted junction, which is nice and strong, and you've done many, many twists, the junction will be measured away from the tip. So just take care. If you get some surprising results that look somewhere between the product and the air temperature, and you've got a twisted pair thermocouple, this is quite possibly what's happening. One of the best ways of attaching the thermocouple is to use solder. I'll be honest, it's a horrible task. Type K thermocouple wire is very difficult to tin. You'll need an aggressive flux to do it, and you should be using a high lead solder, which in an unleaded solder manufacturing environment is also something that many people don't want to use. But there are a number of people around the world using this. It does provide a very repeatable measurement. You can see some of the issues with soldering on that little picture on the right-hand side of the slide, where the wires haven't wetted at all well in that bottom image. And the temperature is actually measured where the two wires touch the metallic solder for the first time. So we're measuring the temperature of the solder bead. So the bigger you make it, the more thermal mass it has, the further away from the real temperature that will be. So it's a very good method. You do need an aggressive flux, a high temperature solder, and try and keep that thermocouple bead as small as possible. Well, an alternative method is to use adhesive. A typical heat-cured surface mount adhesive can be used. And in this image, a blob of adhesive has been applied to the component, the thermocouple wires placed in it. The adhesive is non-conductive for electricity, so the temperature will be measured from the bead of the thermocouple, if you like, that's in the center of the bead of adhesive. In this particular image, you will spot that I was very clumsy and that the two wires are crossing each other before they even get to the component. So I'm likely to be measuring the temperature about 15 millimeters or 10 millimeters to the left of that component. So this is going to measure air temperature. I think you can just see that here. It's likely those two wires are touching, and that's where I'm going to be measuring temperature in this particular case. So take care. Finally, in terms of thermocouple attachment, we see this everywhere. Well, high temperature tape is frequently used. It's excellent when routing wires back from across the board to the data logger. I would suggest you use tape to keep the wires attached to the board. For attaching the tip of the thermocouple, it's not so good. It will lift. You do have to press it very carefully onto the circuit board and the component, press it down to make sure you're going to get some adhesion. If you've got 6 or 10 thermocouples on a circuit board, probably one of them will lift as you go through if you're using this method. It can be improved by using small squares of aluminium tape underneath the high temperature tape. There's articles you can find on the web proposing this method. Just be careful, again, you're going to be measuring the temperature of the aluminium tape junction to the thermocouple, so be very careful to make sure that tape is well pressed onto the legs of the device you're trying to measure. So it's acceptable, but just be very careful when attaching using this method. And here's an image of a typical profiling board. Well, maybe it's not typical. This was one made by me, so it's fairly horrible looking. You can see thermocouples attached to devices, or legs in particular, looking at solder joint temperature, but also onto the body. If you've got devices that are particularly susceptible to a rate of change of temperature or a maximum temperature, you might want to measure package temperatures as well as the solder leg temperatures. This board would go through the oven from left to right as you're looking at it. You can see all the thermocouples are coming off the left-hand side of the board. That would place the data logger and the thermal barrier behind the board, which is good practice. Remember I was saying earlier, we've reduced the thermal mass of the thermal barrier as much as possible, but it will change the zone settings or change the heating characteristics of the oven as it goes through. So always place the barrier behind the circuit board. Typically, a zone length behind it is the best. Moving on, I'm now going to talk about some of the software features. So we've covered the data logger use, the correct use of the thermal barrier to ensure you're not overheating, how to cool down the logger, how to attach the thermocouples, and now it's how you use the software to get the best out of the results you've obtained. There are various software packages available, from the very basic, just for regular oven checking with a time temperature curve, through those that contain some profile optimization or profile prediction, to the professional softwares that have, SPC monitoring and profile or recipe setup and calculation systems within them. I'm going to cover profile prediction, recipe generation, and statistical process control in the next 4 or 5 slides. So this is really an introduction to the topic. I suggest that you go and read up around it afterwards if you're interested in using these features in your day-to-day profiling. So this is an example of a reflow process. So we can see a time and temperature curve. On top of it is placed a template. And in that template are the oven zone settings and the oven zone dimensions. Now they can be seen on this graph as the vertical lines, which denote the end of each of the heated zones in the oven, and the colored horizontal lines, which represent the temperature setting in each of those zones. Setting up this information around oven zones and recipe settings does take a little bit of time to invest up front in what we refer to as a process file. But once it's been done, that unlocks the power of the software to do profile prediction and the recipe calculations. So this enables you to set up the oven much quicker when you come to change product or change processes. So it's worth investing the time up front to put on these, to define these oven zones and recipe settings. So I'm just going to run through the contents of the process file. So it's broken down into 3 parts, as you can see on the left-hand side here. And there are wizards within the software that will step you through setting up these particular items. It's not something you do every day. Most of them are one time. In particular, the oven zones. This is the physical dimension, the physical length of the zones within the oven. So it's something you're only going to set up once. They're never going to change. Typically, you would measure the zones, enter them in the software, and save it with a meaningful name, like, oven number 3 or whatever it is for your particular factory unit. Or there is a library of ovens already built into the software, in which you will find some of the most common ovens in there. The second one on the list is the recipe. Now, at its most basic, the recipe contains the line speed and the temperature settings, which will be used by the software in profile prediction and recipe calculations. It also includes some analysis. The software can automatically analyze the profile when downloaded and check it against a preset number of alarm levels. So you could set an alarm on peak temperature or time above liquidus. And these can be saved separately from the process file, because typically, if you're using the same solder paste on a number of ovens, you'll be checking the same profile criteria. So they can be saved here as a recipe analysis. Third item on the list is the product. This is simply an image or outline of the product being processed, together with the thermocouple positions on it. Now, if you imagine that little circuit board on the bottom left-hand corner is going through from the oven to left to right, you'll see that thermocouple number 3 will enter the hot zone first, and number 1 will be last. So in fact, the peak temperature on number 3 will be reached before that on thermocouple number 1. And the software uses this distance information contained here to correct those peaks, so that when we look at the profile, all of the temperature peaks are aligned. That's standard practice in reflow soldering. So, having invested the time, created the process files so that every time you download your results, you put a process file on them, you then end up with a screen like this on your software. You have a time and temperature graph, some temperature zones with the settings, a picture of the product, and in this case, you've got an alarm. Everything is red, a time above liquidus, in this case 217 degrees, has been exceeded. So what to do? The software contains two possibilities here. One is called profile prediction, and we'll come and look at how that works now. And what this is essentially a virtual oven. So if we click on this, we move on to the next screen. And what we see now is that we have, in addition to the time and temperature graph, we have our oven zone settings listed here. And then we have our new settings. Currently, they're identical. So we're looking at this area here, they're identical to the original settings. And we have 12 thermocouples. We have the 6 originals and the 6 predicted values. And for the moment, everything's the same, nothing has changed. I do now have the option to type in some new oven settings here, so I can try some what-if scenarios. What happens if I change this temperature on zone 6 to 230? At 230 degrees, the software is predicting that I will have reduced my time above liquidus quite dramatically, and some of the heavier components are now within specification, but I'm still getting these alarm values on my predicted profile. So I can try again. I try another setting, maybe this time I'll reduce the 270 down to 260. The software is now predicting that only one of them is out of specification, and in fact it's only out by 1 second. So you can see this is as if you have a virtual offline oven. You can try different recipe settings. The software will calculate, based on the profile that it obtained, what will happen to the circuit board should you try this new recipe. It does take some operator experience to get through that and to try a number of scenarios. Another way to do it would be using what we call easy oven setup. Other companies have different names for this particular function. It's a recipe calculation based on the profile you want to achieve. Again, the starting point is the profile you've just measured on the circuit board. And we're back to that slide again. We have a time and temperature graph, and all of our thermocouples are out of tolerance. If I come across to the easy oven setup, there's an option in here to set up my process limits. So I can now tell the software, I want a profile where my time above liquidus falls between these 2 times. These are my peak temperatures. I want a simple ramp profile, and here's the maximum slope that I can tolerate during that period. And I'm going to allow the software to look at different line speeds. The original line speed on this profile was 45 centimeters a minute. I certainly don't want to go any slower than that, but I'm going to allow the software to choose some options between there to see if there's a better recipe that it can find. So it will go away now and do calculations on a number of different recipes and come back to me and propose some options. So we didn't make the calculation happen. We've just clicked on to the next slide. What I have here is the software proposing some different recipes. And here they are ranked down the side here with line speeds and mean temperatures. This is a kind of indication of whether the recipe is a hotter or colder recipe. Typically, slow recipes have lower temperature settings. And you guys know all this from experience. But this is really to help out people that are having issues when changing or setting up an oven for the first time. Do that initial profile, tell it what you want to achieve, and the software's come back and predicted some settings here. Now, you will notice the first one at the top of the list is now very fast. It's 75 centimeters a minute as opposed to the 45 we were operating at. It does fall within specification. It would allow you to increase productivity. Other options, I think the first option down here at 45, and this shows maybe some of the weaknesses of automated systems. It's showing a very high temperature on this first zone. I don't think that would be realistic for this particular oven. So you do have the ability to edit the recipes. I could come over here and use this as my starting point, edit it, and then I would suggest you do a confirmation profile. The software's proposed these settings, enter them into the oven, conduct a confirmation. You've then got, in your system, you've got the original profile that we started with. We have this prediction that the software is making, and you have your confirmation profile that you've just measured. And in the software, we do have a feature that enables you to overlay one file on top of the other. So you could have the original, the predicted, and the achieved overlaid one on top of the other to be able to analyze them and check that the accuracy, if you like, or the efficiency of the recipe calculation system. Okay, as I said, that's quite a complex topic. It is covered in the help text, and there is a wizard that helps you step through it. It's definitely worth trying out when you're coming to introduce new products. So, excuse me, put the product through once, get the profile, tell it what you really wanted to achieve, and let the software go away and suggest some recipes. So, assuming we've set the oven up for our new product, everything's working well, we're running it day after day, and we want to conduct some trend monitoring. The software has the ability, it's a simplified, I wouldn't say this is statistical process control in all its glory. This is a very simplified trend analysis system. But you can go back and look at the results obtained over a period of time. So rather than a simple time temperature profile for one reflow profile run, we could look back in this example over 20 different files taken over a period of months. And we could look at what was happening, for example, to peak temperature on each of the thermocouples over that time to see whether the oven's gradually becoming cooler or hotter, which might indicate a maintenance requirement. Before we look at this, one thing just to say, if you're using a golden board to obtain this information, be very careful because you may end up measuring degradation in the golden board rather than changes in your oven settings. So before you start any statistical or trend monitoring, make sure that your measuring system is stable. The systems have to be, the measurements have to be repeatable before you can do any analysis. Okay, so assuming we've got a stable profiling tool and we've conducted a number of profile runs, you would probably do this on a fixed recipe. So this might be a daily thing. First thing in the morning, set the oven to a fairly cool recipe, the same setting every day, pass the tool through it, measure the temperatures, and then compare them that way. And the reason I say a cool recipe is that you can then set it to your operating recipe, which will be hotter, and ovens heat up far quicker than they cool down. So we've selected which files. You could select them over a date period or the last 10 files that you've run. The next step within the wizard is to check which of the analysis fields you want to measure. So this could be time above liquidus. For today's example, I've taken maximum temperature. So I've taken those last 20 profile runs. I'm going to look at maximum temperature. The software proposes some upper and lower limits based on the temperature that it finds in the first file. You can override these with your particular control limits that you have on maximum temperature. And then you move on to the results graph. It looks like nothing else that you've seen in the software to date. What we're looking at now, each one of these points here represents a temperature profile taken. So this one was taken, well, it's over a period of months, some years ago. We can see these 20 files, each one of these points represents a pack file. And for thermocouple number 4, this one here, we can see the peak temperature measured each day varies quite dramatically. It's generally below the target, but it does vary up and down. That's got quite a wide variation. If I look at the green trace, number 2 here, I can see that there's much less variation. It's a bit closer to the target temperature, more stable results. And these are reflected down here in the calculated CPK values. So these are measurements of stability of the process and ability of the process to meet the specification required. The exact calculation is detailed in the help text, but you can see here, thermocouple number 4 is a very low value. It's not particularly stable and it's not particularly close to the target. Now, maybe that thermocouple is on the edge of the circuit board and you expect a bit more variability, or maybe it's poorly connected, or maybe it's a twisted junction and we're looking at variation due to the fact you twisted the wires together. So make sure you've got a stable measurement system before you start using the SPC. This graph can be printed out in the same way any other results graph can be in the software. You can zoom in and out. You can hover over any particular set of results. So if you have one set that looks really appalling and you don't want to show it, you can hover, right click and delete it, remove it. The file is still on your PC, but it's no longer analyzed in the graph. One final thing before we go. There is an ability within the software to share results files with other members of your team. You can do this via email. And now we do have a basic viewer available so that if you send the Datapaq file to someone else who doesn't have the software, they can freely download an app. It will run on iOS or Android platforms, and you can do a basic analysis of a graph. You can zoom in and out. You can look at the individual readings, turn thermocouples on and off, and reshare it. You can email it and share it on from mobile platforms. And just to share with you, we are developing this app further. So later in the year, this will make communication with the data loggers via the Bluetooth that I spoke about earlier. So you will be able to reset, download, and do thermocouple checking or real-time readings even using mobile platforms. So we can get rid of the need to carry that laptop PC down to the factory floor every time. You will be able to use mobile platforms to interface directly with the data loggers. Okay, that brings me to the end of my presentation for today. I hope some of it was useful for you. I hope some of the notes around ensuring the loggers are cooled down between use, some of the hints and tips there with the thermal barriers, you'll find useful. And I await Matthias or Stuart to share with me any questions we've had in. Thank you very much for your time.
Yeah, Matthias here. Thank you very much, Rob, for the very interesting and fruitful presentation. From my side, you mentioned a lot of details. what my customers also frequently ask me during my presentations and discussions on site. And additional to my comment, here are the question from the attendees and the community. One is how to make an SPC for a specific temperature, as for example 100 degrees, and it's not the maximum and minimum temperature. Means I think they set up a special point in the software, in the profile, and then they want to do create an SPC report.
So is it that you want to measure the time above 100 degrees or the time taken to reach 100 degrees?
Here it is at, for example, at 100 degrees.
Okay, so in the drop-down menu, which I didn't show, so in the SPC analysis where I chose maximum temperature, within there's a drop-down list, and you can choose, I believe, time above temperature is one of the options in there. And you can, if you've already set that up in your analysis to be 100 degrees, then you could select that time above, and it will give 100 degrees. I can come back with to that particular, the person who asked that question with more detail on that.
Yeah, I think we can discuss that offline. I can do
that, yeah, opening up the software and doing a share with someone.
Okay. There's another question. How accurate are the predicted temperature profiles?
Okay, that's a good one, and I've been asked this many, many times. The profile prediction, we don't guarantee. You won't find on the data sheets a specification for the accuracy, because it depends on the efficiency, accuracy, and maintenance of the oven. For example, if the profile prediction suggests changing a zone from 200 degrees to 220, when you actually change that zone, does it move 20 degrees or does it only move 15? We don't know that. So we can't guarantee that accuracy. Experience shows if you're moving the set points within 15%, then we do get very good correlation is the word I will use between the predicted results and the measured results. And you can overlay one on the other. And the more you use it on any particular oven, the more you'll get used to the difference, if you like, between predicted and what actually happens. It's a bit like a fuel gauge on a car. It's not 100% accurate, but after you've driven it a few times, you get used to the fact that it's not completely linear, and you know how it behaves. So no guarantee, but if you're within 15% of your set points, then you will get a very good correlation, typically within a few degrees of peak temperatures. So it's a great tool for speeding up that up.
Yeah. So test it, use it, and then make your own thoughts about it.
Absolutely, yeah. And it will vary oven to oven, depending on the condition of the oven.
Yeah. Can the same software be used to measure the wave soldering processes?
Yes, as standard, the Datapaq software comes with the ability to measure the wave soldering process. So we don't measure wave depth, but we do have the ability to measure contact times and the preheat curves, and we'll also do the difference between contact times on the parallelism on the wave, and that can be done either with a specific wave palette that we supply, or users can instrument boards, place thermocouples underneath the boards, for example, that will contact the wave and measure it that way. So it's a completely flexible option.
Okay. And the last one is, what is the maximum duration of the thermal barrier in a reflow process?
Okay. That's going to depend on the temperature of the process. So typically, I mean, the thermal barrier we pictured earlier was 25 millimeters high. I think the duration on that is about 10 minutes at the peak temperature in a reflow process. We do have thermal barrier options that are lower in height. So we have 20mm and 28mm. The duration at temperature will vary depending on the size of the barrier. It's noted inside the thermal barrier. It's also noted on the specification sheets you can get from the website. Please check them because it's the thermal barrier that's protecting the investment in the logger. As I say, the 25mm barrier, about 10 minutes at peak temperature. So that is good enough, given that we've got a heat up and a cool down time, that you could do a number of profile runs back to back, or with a 5-minute gap in between to download, and you wouldn't suffer any overheating.
Okay.
But for specific data, you know, go to the guys you see on the screen. They'll be able to help you out, the local RSMs.
Okay, that was everything from the community. So any more questions? So we are already a little bit above our time still.
Yeah, I'm sorry I overshot on that one.
It was really interesting, thank you.
There was a lot to share. So I think I'll hand back to Leonardo.
Thank you, Rob. Thank you, Matthias. As mentioned at the beginning, I will send you all the materials this afternoon. Thank you very much for attending, and in the email I will send you, you will find again also this image with the list of persons you can contact in case you have further questions. Thank you very much for attending, and please check our LinkedIn page if you want to keep updated with the next webinars we have planned. Thank you very much.
Thank you for your time, and any more detailed questions, please feel free to come back to us and we will answer them individually. Thank you. Goodbye.
Thank you, Rob. Thank you, Leonardo.